Hello guys, welcome again to JVM lecture series, and in this video I'm going to show you some practical application and some special cases of calculator technique for the Mohr circle. So let's start with this very easy problem. Determine the normal and shearing stress on section A-A as shown in the figure. So how are you going to solve it? So basically there are two ways to solve it. Number one is by using a simple statistical equilibrium, and number two, by employing the concept of Mohr circle in transformation of plane stress. So to be fair, I'm going to show you both of the solutions that you can use in this problem. Okay, so let's start with the easier one, which is using the basic statistical equation. Okay, so let me draw the free body diagram in my whiteboard first. So what you're going to do here is to isolate this free body diagram in this part of our whiteboard so that you can expose the forces acting internally on section A-A. So it will look like this. So you can actually use this free body diagram, but just for my personal preference, I just use this right part of free body diagram, the section A-A. And then you have this, you have here a 300 kilonewton force here. This is 25 degrees. And then this one, let us put an arrow here to represent the normal force acting on this section area A-A. So this is 90 degrees, of course. We apply the shearing force, letter V. Take note that the normal and shear force should act perpendicular to each other because shear should be parallel to the area section AA. Since these three forces are in equilibrium, we can create a force triangle out of it. You have here a 300 kilonewton force. Let us represent it by a horizontal arrow like this. And then there is a normal force that is going in this direction. Let me call it as N. A shear force that is on this direction. So you should close the figure because our free body diagram is in static equilibrium. Okay? And do not forget that the normal and shear force here is 90 degrees, therefore creating a right triangle. Alright. This angle is technically 25 degrees. And from this force triangle, we can just use simple trigonometry to be able to get the value of N and B. Cosine 25 degrees is equal to adjacent over hypotenuse. So therefore, that is equal to V all over 300 kilonewton. So therefore, we can solve for the value of V, which is equal to 300 cosine 25, which is equal to 271.89 kilonewton. And of course, for N, for the normal force, you can use this. That sine 25 is equivalent to opposite over hypotenuse. So that is N all over 300. Therefore, N is equal to 300 sine of 25, which is equal to 126.79 kilonewton. And then we have to get the normal and shearing stress. Okay? But take note, you should be very careful on the area that you're going to use in dividing these values. Okay? Remember that this is the area that we are considering. So therefore, if you're going to look on this area in 3 dimension, it will look like this one. So, forgive me for my not so good drawing. So, basically speaking, this width is 200 mm. And this is a rectangle whose width is 200 and whose length is equivalent to the length of this diagonal. So, how are you going to get it? This one, this is 25 degrees. This is 100 millimeter. Let me say that this diagonal is length L. So, in looking at this right triangle, sine of 25 degrees is simply 100 over L. So therefore, this length is 100 over sine 25. And that is equivalent to 236.62 millimeter. So therefore, the area that you're going to use is simply 200 by 236.62. So we can now get the normal and shearing stress. To get the value of the normal stress, that is simply equal to what is our normal force? That is 126,790 Newton divided by the area, which is equivalent to 236.62 millimeter multiplied by 200 millimeter. So our unit is Newton per square millimeter, which is, you all know that 1 Newton per square millimeter is technically equal to 1 megapascal of stress. This answer is equal to 2.68 megapascal. So the normal stress on section A-A is simply equal to 2.68 megapascal. And for the shearing stress acting on section A-A, of course, the normal stress should point towards the left direction because our 300 kilonewton is pointing to the right. And of course, the shear force should act downward, somehow downward, to counter the effect of the upward effect of the normal force. To determine the magnitude of the shearing stress, you simply divide this value to the area that we're considering, which is technically 236.62 by 200 millimeter. So therefore, to get the shearing stress on section A-A, that is simply equal to 271,890 newtons divided by 236.62 mm by 200 millimeter. So the shearing stress on section A-A is equal to 5.745 megapascal. And now, how are you going to use the concept of the Mohr circle in solving this particular problem? The first thing that you're going to do if you want to use the Mohr circle is to determine the stress that this 300 kilonewton is producing on this area of 200 mm by 100 mm. So to produce the stress, that is simply force over area. So that's 300,000 Newton over 200 millimeter by 100 mm. Therefore, this one will give us a value equal to 15 megapascal. You have a tensile stress, which is equivalent to 15 megapascal. I'm going to show you both. I'm going to show you the conventional way of doing this Mohr circle and the calculator technique. How are you going to do this? Represent this stress, this problem, using a certain state of stress. You just cut a small portion of the body like this one, and then this one will be our state of stress. Simplify it, this will look like this. So this one is 15 megapascal, and this one is, again, this is 15 megapascal, and this is your section A-A, which is from horizontal, that is 25 degrees. So to avoid confusion, let us name the plane. So let me call it plane letter A, this one is plane letter B, and of course plane letter C. This is that we're going to get the normal and shearing stresses on plane letter C. Again, if you're going to convert it using a coordinate, A has a coordinate of 0, 0 because it contains no shear stress and no normal force. And for plane B, that is 15, 0. 15 being the x-coordinate because x-coordinate is the normal stress. How are you going to use the technique? So let me show you first our calculator. Again, look at our state of stress. You go again to mode number 3, which is stop 3, and that is number 2, which is A plus BX. Looking at our state of stress, the inputs there are force 0, 0, 0, and this one is 15, 0. What did I tell you? Our equation will look like this. Normal stress is simply x bar plus polar, standard deviation x, standard deviation y, cosine quantity ry plus 2 theta. Before doing the calculation, let us again review the rules in using the technique. First things first, the reference plane for this calculator technique should be the plane that contains the higher algebraic value of the normal stress. So, the normal stress on A is 0 and the normal stress on B is positive 15. So, definitely positive 15 is our reference plane. We need the reference plane for the proper sign of theta. So, if you want to know what is the angle towards C, you start from our reference plane B. This one, if this is 25, of course, the complement of 25 is 65 degrees. And from B, you have to rotate clockwise. So, for clockwise, that's negative. So, this theta will be negative 65. So, let us try to use our calculator here. Okay, so, shift, start, 130. And look what happened. Your calculator says mathematical error. Okay, so this is what I'm trying to imply. There is a special case in which our calculator will give you a mathematical error display. The value of R, or the regression coefficient, will be undefined. Let me bring back the data. If the values of Y is 0, both 0, the correlation regression coefficient will be undefined. So, how are you going to use our technique in this kind of situation? Well, you can still use it. You just make a very, very small deviation. For example, 0, you make it just a little deviation so that both of them is not 0. So, you can use 0.0001 here. You can actually put 0.001 here, in any of which you can do so. Let us press AC. And then let's repeat the algorithm. Shift stat number 4. Minus 130. The answer is 2.68 megapascal. Normal stress at C is positive 2.68 megapascal. And then next is to determine the shearing stress. Okay, all you have to do is press this replay button, and then if the cursor is on this location, you will just press delete twice to eliminate X bar plus. And then you move again the cursor, and then if the cursor is located in this location, you just press delete, press sign, press equals. The answer is negative 5.745. So you see the calculator technique is very fast and efficient in this certain kind of problem. But let me remind you again, if the stresses, say for example here 0, 15, if both of the values on Y is 0, you can just put a very small, say for example 0.00001 in any of the values here. You can put it here. You can also put the 0.001 in this entry here, the second 0. Let us now move on to another special case of the problem. The value of R also became undefined if the two values of normal stresses are algebraically equal. Say for example in this problem, determine the major and minor principal stresses. Number 2, determine the normal and shear stress on the 30-degree plane. These two perpendicular planes have the same value of normal stress, which is both tensile stress of 80 megapascal. So basically, the solution is like this. The normal stress and the maximum and minimum normal stress are correspondingly 95 and 65 megapascal. And of course, for the maximum shearing stress, you have 15 megapascal. And let's talk about the normal stress on the plane C and the shear stress on the plane C, which is correspondingly 92.99 megapascal and negative 7.5 megapascal. I'm going to draw again the state of stress. Another case of the Caltech, this is 80 and this is 80. If the situation is like this, how are you going to model it in our table? You go again to stat a plus bx mode, which is you have x and y. So let me call it plane A, and this one is plane B, and this is plane letter C. Letter A will give you what kind of coordinate, that is 80, and since the shear tends to rotate the body counterclockwise, this is negative 15. And for plane letter B, that would give you positive 80 and positive 15, which is, if I'm going to put it here, this will be like this. Okay, so let us show it in your calculator. So that's mode 3, 2. Again, this is 80. This is 80. And this one is negative 15. And this is positive 15. Look first what will happen if I'm going to get the values of normal and shearing stress. Press A, shift 1. Sigma y. Of course, you get the answer 95 and negative 65. So there is no problem here if you just want to get the maximum and minimum normal stress. But this is the issue here. If in case you want to get a stress on any plane at any orientation, this is the first problem. Since both of them are positive 80, you cannot choose which of them is the reference plane. Moreover, if you will try to use the R in the regression, that would be an error. So what is the solution here? Like in the case of the problem in which both of the entries in Y column are 0, we just put a very small increment. You can also do the same thing. So you should put an increment, a very small increment to any of this, so that equal values of x will not happen. We will just give a very small deviation. So you can add a very small increment either here or here. You want to put the very small increment here. So instead of 80, it will become 80.001. So let us go back to our data. Shift number 1, number 2, which is data. That is, instead of 80, we can use 80 plus 0.0001. You press AC. If you want to get the maximum and minimum principal stresses, you go over again with the same way we did before. That is number 4. And then you have a 95.005, which is, if you're going to answer in the examination, the answer is obviously 95. And for the minimum, you have 65.00, which is very obvious that the real answer here is 65. And now you want to get the normal stress and shearing stress on C. So basically, since you make this 80.001, which is actually the stresses on plane letter A, definitely 80.001 is slightly greater. So therefore, since you make this one as 80.001, definitely this one will be our reference planes. For convenience, let us draw a reference line here, which is parallel to this one, so that this plane is also plane letter A, our reference plane. And from this, you have to rotate by how much? This is counterclockwise 30 degrees. Therefore, since that is clockwise, theta is simply 30 degrees. And again, reviewing our formula, that for normal and shearing stress at any planes, that is for normal stress, x bar plus polar sigma x sigma y, you press cosine quantity ry plus 2 theta. And then for this one, that is polar sigma x sigma y, sine of ry plus 2 theta. Okay, let me show you again in our calculators. So since this is theta is positive 30, this one will become plus 60. And then let us check the answer. The answer is 92.99 megapascal, which is the answer before in the conventional Mohr circle. And again, to determine the shear stress here, so again, you delete the x bar and plus sign, and then you delete again the cosine function and replace it with sine, so that the answer is negative 7.5. Negative 7.5 megapascal. Definitely, if you're going to interpret those answer, it means in this plane, since this is positive, the effect is tension, 92.99 megapascal. And since this is negative, the effect is counterclockwise. So, the direction of this should act like this. This is 7.5 megapascal. I hope you get the two special cases in which you can have a mathematical error if you are using this equation. I hope you get it, guys. And now let us now move on to the next video. I hope you subscribe because there are lots of videos coming soon about civil engineering, particularly on some difficult subjects in our CE. Thank you, guys.